All right, this is Brian, and I'm going to do a quick follow-up to the discussion we had in class today on thin film interference, because we had some other kinds of interference in class today, so wasn't able to say everything I needed to, particularly to the folks who are online. So apologies for that. I'm sure the technical difficulties are in the past. So I want to say a couple things about the thin film interference. First off, the situations where we get them are situations where I have some sort of a thin film. And so I've got some sort of a film, and I have light that comes in, and I get light that bounces off the first side of the film, but some of it keeps on going and bounces off the back side of the film. And so I get two reflected rays of light. And I can have constructive or destructive interference between those two. And whether you get constructive or destructive interference depends upon a couple of different things. One thing it depends upon is the wavelength of the light. Two, it depends upon the thickness of the film. And the third thing that it depends upon is the reflective phase changes. Now, this is sort of a subtle thing. When light travels from one medium to another, okay, and you're looking at the reflected wave, if the index of refraction is higher in the second medium, you get a phase change. If it's lower in the second medium, you don't get a reflective phase change. Okay, so those are the two cases right here, your case 1 and your case 2. And so depending on whether you want constructive or destructive, and depending on how many reflective phase changes you have, you're going to use this relationship to solve, or else you're going to use this relationship. Okay, so you have to, when you're solving a problem like this, you have to consider what type of situation you have. Okay, so let's look at the specific case we considered in class today. So we were looking at eye shine in sharks. In the back of a shark's eye, there's this layer of guanine crystals. Okay, and the guanine crystals have an index of refraction of 1.83. Okay, and they're surrounded by cells, which are mostly made of water, and so they have an index of refraction of 1.33. When light comes in, you're going to get a reflection from the first boundary, okay, and you'll also get a reflection from the second boundary. And the question is, those two rays, are they going to be in phase, or are they going to be out of phase? Are they going to be constructive interference or destructive interference? We are looking for the following. If the layer of crystals is 80 nanometers thick, and that's typical, the question asks, what is the longest wavelength for which there is enhanced reflection? So let's go ahead and take a look at how we solve this problem. And the first piece is we strategize, and we want to know, first off, what physics is happening and what is the overall approach. Well, the physics that's happening is I have thin film interference. Okay, so we know that. And if you're doing a homework assignment, you can say this is a thin film interference problem, this is a thin film reflection problem. And then we know everything you know about thin film interference is going to come into play. And then what I'm going to do is this. I'm going to look at the physical situation that we have here, and then I'm going to ask myself, how many phase changes do we have? And the second thing I'm going to look at is, do I want constructive or destructive? What is the situation I'm looking for here? Okay? Now, since I'm looking for a situation of enhanced reflection, that argues for constructive interference. I'm looking for a situation with constructive interference. Do I have, or how many phase changes do I have is the next thing that we need to do. And let's go ahead and do that as part of our preparation step. Okay, so preparation, do we want constructive or destructive interference? We want constructive interference. Okay, and then how many reflective phase changes are there? So let's look at the two rays of light. So the first one comes in here and bounces. It's going through cells which have an index of refraction of 1.33, going into crystals which have an index of refraction of 1.83. So at this boundary, I'm having an increase in index of refraction as I go across the boundary. So therefore, I will have a phase change for the front reflection. I will have a phase change there. Let's look at the rear reflection. The rear reflection, the light is going from guanine crystals with an index refraction of 1.83 into cells with an index refraction of 1.33, it's a decreasing index of refraction. So in this case, I will not have a phase change. Okay? So how many reflective phase changes do we have? Just one. And then what I can do is I can go back and I can look at the relationships and say, given what I've just said about constructive or destructive interference, what I said about how many reflective phase changes there are, I can go back and I can look and see what particular relationship do I want. And the relationship that I want in this case is the second one that we saw, and it looked like this: 2t is equal to m plus 1/2 times lambda divided by n. Now, one other thing to note about this is the index that appears right here in the denominator of this fraction is the index of refraction in the medium where you have the extra travel. So if you look at these two rays of light, the difference between the front reflection and the rear reflection is one of them went through the crystal and one of them didn't. So you're going to use the index of refraction of the crystals here. So this is going to be 1.83. Okay? T is the thickness of the film. That's 80 nanometers, so 80 times 10 to the minus 9th meters. Okay? That's going to be my thickness. The wavelength, that's what I'm looking for. The only question is, what do I use as the value for m? Okay, and that is going to come out as part of our solution. And that's the next step of the process. So let's go ahead and rewrite that equation. And our equation is 2 times the thickness is equal to m plus 1/2 times lambda over n. Now we're solving for the wavelength. And if I solve for the wavelength, I get this. Wavelength is equal to 2 times t times n divided by m plus 1/2. Okay? That's my basic relationship. And remember what I use for the different values. For the index of refraction, I'm using the index of refraction of the crystals, that's 1.83. For the thickness, that's 80 nanometers, so that's 80 times 10 to the minus 9th meters. What do I use for m? Well, I'm looking for the largest possible value of lambda. So if I want the largest possible value of lambda, I want the smallest possible value of m. And the smallest possible value I can have is just m. M is equal to 0. So if I complete my calculation that way, I just get this. I got the wavelength is equal to 2 times t times n divided by 1/2. And I know everything in that relationship, so I can go ahead and do the calculation. And if I do that calculation, I get 590 nanometers to 2 significant figures. Okay? And what part of the spectrum is that in? Well, that's in the yellow region of the spectrum, okay? That's kind of like I'm getting out towards the reds. I'd say it's kind of in the yellow part of the spectrum. And for my assessment, I'll say, oh, if I look actually at the reflection from a shark's eye, if I look at its eye shine, what I get is yellow. And so my assessment is, yes, my calculation does match my experience of the way the world works. And that's the type of problem we're going to be doing when we're looking at thin film interference.